Hello everyone, welcome to EEEE Lecture number 12A. Today we are going to start with module number 2, that is AC circuits. So in module number 2 we have unit number 2.1 where we'll be discussing about generation of alternating voltage. We'll study about average value, RMS value, form factor, phasor representation in rectangular and polar form, and about the crest factor. So let's begin with today's topic. So first of all, we'll define the alternating current. So when the current in the circuit varies in magnitude as well as direction periodically, it is called as alternating current. Similarly, we have alternating voltage. When the voltage in the circuit varies in magnitude as well as direction periodically, it is called as alternating voltage. All right. So these are the two examples of a sinusoidal alternating voltage and sinusoidal alternating current. That is AC current and AC voltage. All right. I think we have seen this. We have in module number 1 we have seen DC. So for a DC, we have a constant with respect to time. So this is the voltage over here, okay, and this value will remain constant. Whereas in AC, it will periodically change. And this is my one period over here when it completes one cycle. This is the period of the AC waveform. So this is my AC input. My AC sinusoidal AC voltage and sinusoidal AC current. All right, and my x-axis is omega t. Now, the circuits in which alternating current flows are called as AC circuits. So this module number 2 is all about such AC circuits. All right, and now what are the advantages of this AC? So voltages in AC systems can be raised or lowered with the help of transformer. All right. Then it's used in AC motor, which is simpler and have lesser maintenance. AC voltage can be easily converted into DC. Therefore, AC is extensively used in practice. So let's see the advantages. AC is extensively used in practice. So all your single phase supplies in at your residential areas are having the voltage rating of around 230 to 250 and frequency of 50 hertz. All right. So these are the advantages of AC voltages. Okay. Next, we talk about generation of alternating voltages. So, AC voltage or alternating voltage can be generated either by rotating a, so here it is, either by rotating a coil in a stationary magnetic field or by rotating a magnetic field within a stationary coil. So these are the two techniques. I repeat, AC voltage can be generated either by rotating a coil in a stationary magnetic field or by rotating a magnetic field within a stationary coil. So in both the cases, your magnetic field is cut by the coils and an EMF is induced in the coil according to the Faraday's laws of electromagnetic induction. So let's see the scheme for the generation of AC voltage. So let me minimize it. Yeah. So we have over here, we consist of a permanent magnet with two poles. So here we have north pole and a south pole. A rectangular coil of n turns. Rectangular coil A, B, C, D, P, Q of n turns is rotating in anti-clockwise direction. Okay, and with angular velocity omega. So this is my angular velocity omega. We have a prime mover which rotates this rectangular coil with angular velocity omega radians per second in a uniform electric field. So we have this electric field, right? So what will happen is, because of this electric field, yeah, this will be lines which will be cutting. So every time the coil rotates, it will cut the, so every time the magnetic the coil rotates, the magnetic field is cut by the coils and an EMF is induced in the coil. All right. So when the coil cuts the magnetic lines of flux, so these are the magnetic lines of flux. Magnetic lines of flux. All right. So when the coil cuts the magnetic line of flux, an EMF is induced in the coil. An EMF is induced in it. So let phi m be the maximum flux cutting the coil. Okay, so let me see. So this is the scheme, right? So we have a north pole and a south pole, two poles, and we have a rectangular. This is my coil. So this blue color is my coil, rectangular coil. Sorry, this is my coil, it is moved with the help of a prime mover in anti-clockwise direction with omega radians per second angular velocity. All right. So let us simplify this picture. So what I have shown is I have shown the 1D picture of it, the front view of it. So you only see this is the 2D picture. So you only see from the front side only a strip. All right. So these are the magnetic lines of flux which are shown in orange color. So from north pole to south pole. So we have marked the direction, the axis as y dash, and x dash is the x axis. So let phi m be the maximum flux cut in the coil when its axis coincide with x dash axis. So when the coil is moving along y dash, that is parallel to the lines of flux, the flux linkage within it is zero. All right. So when the coil is in this direction, so let's see that if these are my magnetic lines of flux and my coil is also oriented in parallel with it, all right, then a magnetic flux linkage will be zero. Okay. When it will be, so here phi will be zero. So when phi will be maximum, so here are my magnetic lines of flux. So it will be maximum when it is perpendicular to it. So here it will be phi m. All right, I hope it is clear. This black color line which I have drawn is the coil. So this is the coil over here. All right, it makes an angle theta with x dash axis, and it is rotating in the anti-clockwise direction. So this coil is continuously rotating. Okay, so when the coil is moving along y dash, the flux linkage with it will be zero. So here it is will be zero. Coil rotates to an angle theta equal to omega t. So coil rotates with an angle theta equal to omega t, where omega is the angular velocity with which the coil rotates. So where theta is the angle between the motion of the coil and the direction of the magnetic field. Okay. So now the flux linkage of the coil is given by, let's see that this flux linkage in the coil is given by phi is equal to phi m cos omega t, or we can write it as phi is equal to phi m cos theta. So as per the Faraday's laws of magnetic induction, so whenever the coil cuts the magnetic lines of flux, there will be a EMF induced, and this EMF is given by E is equal to, it is represented by, EMF is represented by E. So this is my EMF. E is equal to minus N d phi by dt. What is N? N is the number of turns. Number of turns. Okay. This rectangular coil is rotating by for n turns. Let's say it's rotating 100 times. So N is 100. Okay. So we have n turns. So E is equal to minus N d phi by dt. What is phi? Phi is equal to phi m cos omega t. So it will be d by dt of phi m cos omega t. Phi m is a constant, so we can take it out. So we have over here differentiation of a cos will be minus sign. So your minus sign will go. So we have E is equal to n phi m omega sin omega t. Okay. And here we remember that omega t is equal to theta. So now n phi m and omega we term it as em. Okay. So what is em called as? Em is n phi m omega, which is the maximum value of induced emf. Okay. So E equal to n phi m omega is the maximum value of induced emf. And what is E called as? E is the instantaneous value of the induced emf voltage. Okay. Instantaneous means at every instant of time we can calculate the value of E. All right. So E is the instantaneous value of the induced EMF in the coil. Now, as per this equation, E equal to Em sin omega t or sin theta, EMF depends upon theta or the angle, right? As the coil rotates continuously with a constant angular velocity, where omega t varies from 0 to 360 degree, the magnitude of induced EMF in the coil varies continuously. So what we are saying is, if theta changes from 0 to 360, E also changes, the EMF also continuously changes, varies continuously. So let's see an example. So if theta is 0, there is no EMF produced, and E will be 0. When theta is 0 to 360, the coil completes one rotation. So let's take different instance, that is position of the coil, and we calculate the induced EMF as follows. So for theta equal to 0, in this equation E equal to Em sin omega t, we'll be using this equation. So sin 0 will be 0, so EMF will be 0. Next, if theta is around 90 degree, omega t is pi by 2, so we have sin 90, and sin 90 is 1, so EMF induced will be maximum, which will be Em, and we have said this before. All right. Now if theta is 180, Sine of 180 will be 0. Again, the EMF induced will be 0. If theta is 270 degree, sine of 270 degree is minus, value. So minus 1. So E will be minus of EM. And if theta is 360 again, sine of 360 is 0 degree. All right. Now, if we plot all these instances, so let's say at 0, it is 0. For pi by 2 or 90 degree, it is EM. For 180, it is 0. For 2 to 270 degree, that is 3 pi by 2, it is minus EM. And for 2 pi, it is 360. Now, if we plot all these points over here like this, if we plot all these points, if we join them together, you'll get a sinusoidal waveform. So that is how alternating voltage is getting generated. All right. So we have a simple, again I repeat, we have an arrangement of permanent magnets. Okay, so permanent magnets, we have magnetic lines of flux which are directed in y dash, and we have a rectangular coil rotating in the anti-clockwise direction with an angular velocity omega. So whenever this coil cuts the magnetic lines of flux, a EMF is induced, and that EMF is given by E is equal to EM sine omega t. All right, and this value of induced EMF changes continuously. So it's an instantaneous value. So this is the plot of E versus omega t or theta. So as you can see, carefully, from 0 to 2 pi, it completes a one cycle. Okay. So this is how we generate a alternating voltage. So, by plotting the EMF, induced EMF against the positions of the coil, position of the coil is theta. We get the sinusoidal alternating waveforms as shown in this diagram. Therefore, the alternating voltages can be generated by rotating a coil with constant angular velocity in a uniform magnetic field. All right. So if they ask you the question based on explain the generation of AC voltage, you have to explain it up till here. Okay. You can give this example also, and we have to derive this equation also. EMF induced will be E is equal to EM sine omega t. I hope it is clear now. Okay, let's move on to the next topic. Let's move on to AC terminology. Okay, so since we are dealing with the AC voltages, there will be a lot of new terminologies which will be associated with the AC, waveforms. So first is instantaneous value. The value of the alternating quantity at a particular instant of time is called as its instantaneous value. So let's say in this diagram over here, we have a sinusoidal voltage where y-axis is my voltage, instantaneous value of the voltage, and x-axis is theta or omega t. So at t1, what's my value of v1? At t2, what is my value of v2? So my v1 of t and v2 of t2 is my instantaneous value. Okay, so I can calculate the value of voltage at any instant of time, and that is called as instantaneous value. Okay, so the value of the alternating quantity at a particular instant of time is known as its instantaneous value. I hope it is clear. Okay, next we go to cycle. So one complete set of positive and negative values of alternating quantity is known as a cycle. So in this waveform, this is your positive value, the AC input is positive, and here the AC is negative. So one complete such set of positive and negative values of alternating quantity is known as cycle. So this is my one cycle. This is one cycle of sinusoidal AC voltage. Next is time period. The time taken by the alternating quantity to complete one cycle is known as its time period. Okay, so the time for one cycle will be seconds per cycle. So let's see the first waveform. In the first waveform, the waveform repeats itself after one. Okay, after the time instant 1. So this will be my period. Okay, now this is a sinusoidal waveform. It completes positive and negative half over here at 2. So till 2, from 0 to 2, it will show me your period. So one period is when the cycle repeats itself. So let's say we have this waveform. So here the period will be here. Okay, this much. Now let's say if we have another waveform. Now let me know the period over here. Okay, this is 1, this is 2. So what is the period of this waveform over here? So the waveform repeat itself after 1. So this will be my t period of the AC quantity. All right, I hope it is clear the time period. Now next is the frequency. The 1 upon time period will be giving me the frequency. So basically the number of cycles completed by an alternating quantity per second is known as frequency. It is denoted by small letter f. It is measured in cycles per second or hertz. Okay. The frequency is the reciprocal of the time period. So let's say we have a AC signal with a frequency of 50 hertz. That means the time period will be 1 upon 50. That will be 20 milliseconds. So again, frequency will be 1 upon reciprocal of time period, and its unit is hertz. It's very important to understand this, and that this is a very important relationship. Okay. Okay. Next we go to amplitude, the maximum positive or the negative value of an alternating quantity. So let's say the AC quantity starts from 0 and it reaches a maximum value at Vm. So my Vm is my Vm to minus Vm. It reaches the positive to the most negative part. So my amplitude of this signal will be, for the positive part it is plus Vm, for the negative cycle it is minus Vm, and the total peak to peak value will be twice Vm, okay, from year to year. All right, so this is plus Vm, this is minus Vm, and that's the amplitude. Now let's discuss about the phase. The phase of an alternating quantity is the time that has elapsed since the quantity has last passed through the zero point of reference. So let's understand this by a phase difference phi. So I have my waveform VA. It is denoted by Vm sine omega t plus theta plus 0 degree, and VB starting earlier by an angle phi. So VB is actually Vm sine omega t plus phi. So is there a phase difference between VA and VB voltages? Yes, there is. So there is a phase difference between VA and VB, and that phase difference is phi. So let's say that two alternating quantities are said to be in phase when they reach their maximum and the zero values at the same time. Now these are VA and VB. For VA and VB, they do not reach the maximum. They reach the maximum at the same time. They are not reaching the maximum as well as the zero values at the same time. So they are not in phase. Okay, so we are, here we can say that VB leads VA by a phase angle phi, where phi is the phase angle. Okay, all right, understood. So VA is written as Vm sin omega t plus 0. So this we can add it as plus 0 degrees. All right, and oh, sorry, here it is. And VB is Vm sin omega t plus phi. So actually the voltage VB, it's leading the VA by angle phi. All right. Okay, understood this? Now we write the standard form of alternating quantities. So let's write it down. So it is given by, let's write first in terms of voltage. So V is given by, normally we have derived E, right? EMF is EM sine omega t. Now for a voltage, it can be written as V is equal to Vm sine omega t, which can be written as V is equal to Vm sine theta, where theta is equal to omega t. Now this can also be written as Vm sine, what is omega t? 2 pi f. Okay, t. All right. So, since we have over here omega is equal to 2 pi f. All right. It also can be written as Vm sine. Instead of writing f, we can write 2 pi by t into t, because we know f is equal to 1 upon t. So these are all the standard forms of alternating voltage. So let me highlight it. This represents all the sinusoidal AC voltages. So these are all AC voltages standard form. Actually, we should have written omega t plus 0 degree. That's the standard form. All right. And what do we know over here? We know that omega will be equal to, if we compare this one and this one, omega will be equal to 2 pi by t, and theta is omega t. So these are also the important relationship, and is representing which waveform? This waveform over here. Let me highlight this. Okay, so this is my voltage V. This is theta equal to omega t. This will be pi, 2 pi, 3 pi. This maximum value will be Vm, and this value will be minus Vm. Okay, so this is my AC voltage. Similar to it, we can write it for AC current, alternating current. So it is given by I equal to Im sine theta. We can rewrite it as I equal to Im sine omega t. Now instead of omega t, we can write it as I is equal to Im sine 2 pi f into t.
All right, then I is equal to Im. Instead of f, we can add it as 2 pi by t into t. Okay, so here theta is omega t, over here omega is 2 pi f, and over here f is 1 by t. So these are all the standard forms for alternating current. This represents AC current. All right. Diagrammatically, if I want to represent the AC current, it will be like this. Same sinusoidal nature. This is I, this is omega t, and we represent the current in this form. Okay. This is pi, 2 pi, 3 pi, and 4 pi, and so on and so forth. So these values over here will be Im, and here it will be minus Im. All right. So these are all the standard forms of alternating quantities. In the numericals, which we are going to solve now, all the standard forms are required. All right. So this is the end of lecture number 12A. Now let's go to 12B. So we have studied in 12B, 12A that the standard form of AC voltage sinusoidal and AC current is given by this formulas. Okay, AC voltage in these are the standard forms we have just now seen. And let me write the date. All right. So we have just revised that standard forms of alternating quantities, and we can define the how does the waveform look like. The waveform looks like a sinusoidal voltage like this. This is omega t, this is V, the maximum value will be Vm, the minimum value will be minus Vm. Okay, here it is, and this is my AC voltage. And these are my standard forms. V is equal to Vm sine theta, sine omega t, sine 2 pi f t, and sine 2 pi by capital T into t. Okay, where capital T is the time period. Now, it's requirement for the numericals that we convert radians to degrees, and we know the conversion from degrees to radians. So let's say that pi radians is there. Okay. Now pi radians means 180 degree. So we want to convert this pi into 180 degree, and what's the formula? Pi we multiply by 180 by pi. Okay, and that becomes 180 degree. Let's take another example. Let's take pi by 4. So pi by 4 is how many degrees? Okay, so what we do? Pi by 4 we multiply it by 180 by pi. And if we see carefully, it will be 45 degrees. Let's take another example. Let's say we want to calculate pi by 3 is how many degrees. So pi by 3 we multiply it by 180 by pi. And if you see carefully, this will be 60 degree. I hope it is clear. I hope it is clear. The radians to degree conversion is you multiply the radians by a factor of 180 by pi. Okay. Now let's convert 90 degree to how many radians. So for this 90 we multiply by pi by 180. So this becomes pi by 2 radians. I hope it is clear. Then 270 is how many radians? So 270 we multiplied by pi by 180. So this comes out to be 3 pi by 2 radians. Okay. So here the conversion factor is pi by 180. So if we want to convert degree into radians, multiply the degree into pi by 180. That will give you the value in radians. Okay, we can do that in calculator, but just in case it is required. So let's solve one numerical on AC quantities. So write down the numerical. Okay, let me take the pen. Numerical number 1. So let's write along an alternating quantity, an alternating current I is given by I equal to 141.4 sine 314t. Okay, so that's the value of I given to you. We need to find A, the maximum value, B, the frequency, C, time period, and D, instantaneous value of I when time t is equal to 3 millisecond. So we need to find the maximum value, the frequency, and the time period. So let's start with the solution. So let's rewrite this I in the standard form. So standard form is I is equal to Im sine omega t. Now if we compare this with this 141.4 sine 314t. If you compare this equation number 1 and 2, what do we get? We get the value of Im as, so we can write over here the maximum value, which is nothing but Im, is 141.4 amperes. Straight away, it's a clear cut answer. Okay. Next, we can calculate the frequency. So basically omega is given as, if we compare equation number 1 and 2, omega is 314. And what is omega given by? 2 pi f. 2 pi f is 314. So frequency will be 314 divided by 2 pi. And this will come out to be 50 hertz. So the answer is 50 hertz. The frequency is 50 hertz. Next, we have to calculate the time period. So we know the frequency, time period will be 1 upon frequency. So 1 upon 50. Let me rewrite this as frequency f. So 1 upon 50 will be around 20 millisecond or 0.02 seconds. Alright, we got the time period. Now we have to calculate the instantaneous value when the time is 3 millisecond. So let me rewrite this. I is equal to 141.4 sine of 314t. Now this is written as sine omega t. But in actually, if we want to calculate this value, we need to convert. And the time is given. T is given as 3 millisecond. So it is 3 into 10 is to minus 3 seconds. All right. So what I'm saying is we need to convert this. I'll rewrite this as follows. So I is equal to 141.4 sine of 314. Now this is in radians. We'll convert it into and multiply it by 3 milliseconds. Now I want to convert it into degrees. So I'll multiply it by 180 by pi. And that becomes in degrees because it's easier to calculate this way. So I will be 141.4 sine of, if you calculate this, it will be 53.97 degrees. Okay. So here if you calculate the value of sine of 53.97, you will get it as this answer as 114.36 amperes. So this is the value of, this is the instantaneous value of I when t is equal to 3 millisecond. So this is how you calculate the instantaneous value of AC quantity, that is AC current. And that's all for this lecture. I hope we have made the concepts clear to you. First we have discussed about the generation of AC voltage. Okay, then the standard form of AC quantities in voltage or current, AC voltage or current. Then we have seen the various terminology, AC terminology, and we have solved one numericals on the based of the standard form of alternating quantities. So that's all for today. Next time we'll continue with further topics. Until then, have a good day and thank you.